I am Dr. Anantaya MB, Professor and Head of Civil Engineering Department, SUIT, Bangalore. Today we will see one problem on deflection of cantilever beam using conjugate beam method. It is of Module 3 of Subject Analysis of Determinate Structures. Determine slope and deflection at free end of the cantilever beam shown in figure below. EI is constant throughout. Here I is same. I is same. See, the beam is shown here. A to B is 3 meter, B to C is 2 meter, this point is B, this point is C, this is the free end, means we have to find slope and deflection at point C. As first step, we have to calculate the bending moment at various points C, B and A. See, bending moment at C, it is the free end, that should be equal to 0. What is the bending moment at B? See, this is the section line, we have to consider right portion to this B. So, this 10 kN will have a moment of 10 into 2. Clockwise is negative, therefore minus 10 into 2, 20 kilonewton meter. The moment due to this 5 kilonewton load is 0 because it is acting at the same point, distance is 0. Now we have to calculate bending moment at A. This is the section line. I have to consider this full beam. Therefore the moment is 10 kilonewton, moment is 10 into 5. It is clockwise minus 10 into this distance 5. Minus this also minus clockwise 5 into 3. 5 into 3 it is minus 65 kilonewton meter. So this is the reference line ABC on which bending moment is 0. Here minus 20 means downward 20 at B. At A is 65 kilonewton meter. All these values are negative. So this is called bending moment diagram. For conjugate beam method we want M over EI diagram. For both moment area and conjugate beam method we have to calculate M over EI diagram. M over EI diagram is nothing but we have to divide it by EI. Since flexural rigidity is same EI only, therefore it is 20 by EI and 65 by EI. Same is M over EI diagram, provided we have to divide this bending moment values by EI. For calculation purpose, I am drawing a horizontal line here. Here I am dividing one rectangle, one triangle, one more triangle. So we know this is 20 by EI, therefore this height is also 20 by EI. Then remaining is 65 minus 20 by EI is 45 by EI. Now we have to, in conjugate beam method, we have to draw conjugate beam. Conjugate beam is a imaginary beam loaded with M over EI diagram. Now what I am doing, see this is the cantilever beam. Here it is fixed end becomes free end becomes fixed end. C is free in the given problem, but in conjugate beam this is fixed. A is fixed in the given beam, therefore A is free. Then I have to take this load and keep over this beam as load. M over EI diagram become the load. There are one rectangular load, one triangular load, one more triangular load. I marked all the CG values for calculation purpose. This is the triangle from apex. CG distance is from here 2/3 of 2. 2/3 of 2. From here to here remaining is 1/3 of 2. Similarly for this triangle it is from here 2/3 of 3. This distance is 3. From here 1/3 of 3. Again it is a rectangle, it is at the center. 3 meter means 1.5. This is 1.5 meter. 1.5 meter. Now I marked all the CGs of this diagram. This is called conjugate beam. Conjugate beam. Now I have to calculate slope at C. See, for the given beam A end is fixed. In conjugate beam this is free. Free end becomes fixed end. Already we discussed about that. Now see, this is the deflected shape or elastic curve of the beam. This is deflection delta C. This is the angle theta C or slope theta C we have to calculate. First we will calculate slope at C, that is theta C. See, first conjugate beam method or theorem tells slope at C in original beam should be equal to shear force at C in the conjugate beam. Shear force at C dash in the conjugate beam. I am marking this is A as A dash, B is B dash, C is C dash in the conjugate beam. Then therefore what is the shear force? Now this is the section. I am moving from right to left. All these loads, the bending moment diagram is downward, means I am treating all the loads are acting upward. Therefore this upward all loads are plus. The area will give you the load 3 into 20 by EI plus half into 3 into 40 by 5 by EI plus this triangle half into 2 into 20 by EI. I got theta C equal to 147.5 by EI. Directly we are getting the slope. Now we have to calculate this deflection at C. The second conjugate beam theorem tells deflection at point, a given point in original beam C should be equal to the bending moment at C dash in the conjugate beam. Bending moment means already we know the shear force into CG distance. We have to multiply for all the areas. You see, first this is the rectangular load. It is acting upward clockwise. Therefore, it is plus. Area is 3 into 20 by EI. 3 into 20 by EI into its CG distance is 2 plus 1.5. 2 plus 1.5. It is 2 plus 1.5. This is the CG distance. Plus the area of this half into base into height. It is half into 3 into 45 by EI into its CG distance from C is, see, from here to here 2 plus 2/3 of 3. 2 plus 2/3 of 3. Next, plus this triangle. What is the area? Half into 2 into 20 by EI. Its CG distance from C dash is 2/3 of 2. Half into 2 into 20 by EI into 2/3 of 2. Because what we did here, area into its CG distance plus area of this triangle into its CG distance from C dash plus area of this triangle into its CG distance square. If I add total, I am getting the deflection at point C, that is 506.6 by EI.